Hi. Well, thank you all. It's great to be here. I gave a talk at CERN a while ago, and I think there's a lot of interest in the physics community for what we're doing. And so in this talk, I wanted to put a particular spin on what we're doing to emphasize how it might play into machine learning, because I think that's your primary interest. So I'm from D-Wave, and oops. Yep. So we have a pretty ambitious mission. We want to tackle the world's hardest computational problems, particularly in the fields of AI and machine learning, because we think that that's the field that our particular architecture of a computer is most suited to helping. Our technology is based on superconducting processors that use a type of quantum computing called annealing. I'll talk about that. And we've now started integrating the quantum computers into a hybrid classical quantum computing architecture. So you can actually tap into quantum computing resources from architectures with which you're very familiar. And our business model is we actually sell quantum computers. We've sold several around the world to Google, to Oak Ridge, to Los Alamos National Lab. Oak Ridge has recently just bought some cloud services to our machines. And we also are about this autumn to start selling quantum enhanced machine learning services. So hopefully some of you guys can play with that. So what are quantum computers? So very simply, they're computers that tap into physical effects that we don't conventionally use in regular computers. So the most important effects are, first of all, superposition. The idea that if a bit in a regular computer is a 0 or a 1, in a quantum computer it can be partly 0 and partly 1 at the same time to different degrees. And we use this effect significantly in our machine because whenever we start off the computation, we always started in the same state. We started in equally weighted superposition of all possible bit string we can make in n bits. And our current machine has 2,000 qubits. So the starting state is a superposition of 2 to the 2,000 components, which is enormous, because this is vastly more components than there are particles in the known universe. You couldn't possibly imagine representing such a state explicitly classically. The other effect we use is entanglement, and in a computational context, the idea is that usually in a regular computer, you would think that if you perform an operation on one subset of the bits in your memory, you wouldn't change the state of the other bits that you don't touch. But in a quantum computer, if those quantum bits are entangled, that's not true. If you perform an operation on one subset of the qubits, you can actually change the state of other qubits, even if you're not directly operating on them. And this mechanism gives you a new way of devising algorithms that work in a fundamentally different way from all classical computers. And the third effect that we make the most use of, I would say, in our particular approach is tunneling. So the idea here, again, in the computational context, is if you have a solution search space characterized by different bit string candidate solutions, usually you would think to have to apply some kind of energy to flip bits to go from one solution to the next. But in a quantum computer, you can actually tunnel through those energy barriers, and so you can move around these search spaces energetically extremely efficiently. And this tunneling is coherent. It occurs at the scale of many, many qubits co-tunneling at the same time. And you can actually explore the entire solution space in a fundamentally new way that you can't do with any conventional algorithm. So those are the three primary quantum effects that we and other people use in quantum computers. Amazingly, there's many different ways you can put those things together to actually make a functional quantum computer. So if you've been following the news lately, there's most emphasis today is on a type of quantum computer called a gate model quantum computer. This is the idea that you start with a Boolean logic gate, and instead of having classical gate operations like NAND gates, you have operations that work on quantum bits. And this is a very much favored model amongst theorists for quantum computation, because you can prove all sorts of theorems and properties about these gate model machines. In particular, if you have a particular set of gates, you can prove that you can do any quantum computation in principle. And more importantly, theorists have worked out a complete error correction scheme for this kind of quantum computer. So this is why companies like IBM and Google and Intel have started developing quantum computers based on the gate model. The problem is that currently the most efficient error correcting codes we know of for this kind of machine require a truly enormous number of physical qubits to give you one robust logical qubit. It's of the factor of thousands of physical qubits, are needed in error correction to give you one robust logical qubit. So for that reason, D-Wave decided that wasn't the model we were going to implement, at least not first. The other model, which is a local favorite, is an approach to quantum computing called topological quantum computing, pursued by Microsoft. Now, this is also a gate model scheme, but the idea is it uses a kind of quantum quasi-particle, a non-abelian anion, which in principle you can use to perform universal quantum computation just by braiding these particles around each other. And the phase that you accumulate is a function of the number of times one particle winds around another, but not the trajectory taken. And because of this property of these hypothetical quasi-particles, you can, in principle, do gate model quantum computation without explicit error correction. That's why Microsoft likes this scheme. Unfortunately, there's some recent work that came out in January this year that shows that if you have manufacturing imperfections in the materials needed to create these quasi-particle excitations, the excitations don't actually have all the topologically protected properties you wanted. So that, to us, again, looks like quite a difficult scheme to achieve. So the scheme that we pursued is called an annealing approach, and Google is also making an annealing machine, as is IARPA, which is the intelligence agency's version of DARPA. And the nice thing about annealing is it really harnesses a natural ability that quantum systems have to sort of find low-energy configurations efficiently. Although it's not fault-tolerant, it's intrinsically quite resilient to error, so it performs quite robustly, even in the presence of some degree of noise. And we don't need very, very long coherence times to achieve this kind of model of quantum computation, which is a big distinction from the gate model scheme. The current machine that we make is not a universal quantum computer, but in principle it could be made universal just by adding one additional coupling term we have in there. So those are the three popular schemes at the moment. The theory behind our scheme really comes back to a very old theorem of quantum mechanics. I think it's from the 1940s. It says if you start a quantum system off in its ground state and you slowly perturb the parameters of the system to bring it into a new Hamiltonian, then the system will stay in the ground state of all the instantaneous Hamiltonians passed through. And around 2000, a professor from MIT, Ed Fahey, he had the idea that if you make the final Hamiltonian be ones that encodes a computational problem, such that the ground state would represent a superposition of all global optimal solutions, you could use this theorem to basically design a computer that worked in this adiabatic way. And so as you start the system off, you start from some initial Hamiltonian here, and the coefficient of that Hamiltonian has to be large. And then as you go through the annealing, you reduce this coefficient while ramping up this coefficient. And that's exactly what happens in our hardware. This is what we do physically to drive this computation forwards. So the theory is that if you start off in the ground state of one Hamiltonian, and you slowly change the A and B parameters so that you end up with all B and no A, you should get an optimal solution to the problem. And the time it takes to do that computation is supposed to scale as the inverse square of the minimum gap between the ground state and the first exciting state. That's the theory. When you build this machine, it's not what we find happens. And the reason it doesn't happen is that this theory, this idealized model of computation, assumes that you work at absolute zero, so 0 Kelvin. And our machine is very cold. It operates at 15 millikelvin. But it's not absolute zero. So there are actually thermal effects that bump you out of the ground state as you go through this. And the rate of transition from the ground state to the other states decreases as you go through the annealing. And at some point you get a freeze-out effect. And then when you read the state here, you can be in any one of these low-lying states. So what you actually get is not a guaranteed ground state, but some low-lying state according to some distribution. Now, initially, when we were thinking of the machine as an optimizer, this looked like a problem, because this is the state we wanted to find a global optimum, and these would be all error states, essentially. But we've now come to realize that the distribution of these states at the end of the annealing is quite close to Boltzmann distributed. And to make a machine that will give you naturally samples from a Boltzmann distribution efficiently is actually a very difficult thing to do classically. And so this actually has a lot of applications in machine learning because of this. This, in fact, is a feature now that you can sample from the low-lying states, not just the global ground state. So this is what our current machine looks like. It's a very large box. It's about 3 meters by 3 meters by 3 meters. Inside the box, if you were to take away all the shielding, you'd see this cryostat, which has a series of plates that step down the electronics from room temperature all the way down to 15 millikelvin. And this entire assembly here, with the quantum process at the very bottom, is about 10 kilograms of metal cooled to 15 millikelvin. It's 180 times colder than interstellar space. We also evacuate the chamber around the machine, and we shield it from all radio frequency and magnetic noise. It's an extremely exotic environment we have to create to turn on quantum computation. The chip itself sits on this chip carrier. It's about 1 square centimeter, so it looks just like a regular computer chip. The difference is, you can see it's made of a material called niobium, which is a superconductor at the temperature that we operate the chip at. And although it's a superconducting processor, we actually make it in a regular CMOS foundry. So we use a foundry that they make Intel chips in to make this quantum superconducting processor as well. And our current processor, it's about 2,000 qubits and 300,000 Josephson junctions, which is by far the most complex superconducting electronics device created for computation so far. The physics of what goes on is actually quite simple. The qubits can be thought of as a spin up, spin down, plus or minus 1. And you can program the chip by giving parameters h and j that sets the bias on each qubit to either want to be more spin up or spin down, and the coupling on pairs of qubits that are directly wired together to be ferromagnetic or antiferromagnetic. So all computations you want to express are fundamentally mapped into a problem of this quadratic form. And then when you run the annealing, you get a bit string vector out that corresponds to one of the low-lying energy configurations of bit strings that would minimize that function. And if you don't like plus or minus 1 variables, you can change to Boolean variables very easily. And as I said, at the end of the annealing process, after the dynamical freeze-out has occurred, the distribution of those spin vectors is close to Boltzmann distributed. And in the middle of the annealing, while all the quantum mechanics is sort of fully turned on, the distribution of those states is very close to quantum Boltzmann distribution. It's a different distribution. And so using this Boltzmann distribution, we can use this device to drive probabilistic machine learning models such as Boltzmann machines, or restricted Boltzmann machines. And using this quantum Boltzmann distribution, we can create entirely new classes of machine learning models called quantum Boltzmann machines. This is very exciting because if your data has within it statistical correlations that are of a quantum mechanical origin, it is quite possible a quantum Boltzmann machine would be more naturally suited as a way of sort of learning the properties of those correlations. So I'm pleased to say that we've got a lot of evidence now that we really have created a functional quantum computing system. We've demonstrated the presence of all of the 3 main effects in quantum mechanics: superposition, entanglement, and cotunneling. Our friends at Google showed that not only are those quantum effects present, but they're actually playing a functional role in the computation of the chip. They show that in that paper. We've had our critics along the way, particularly from IBM. But all of the classical models so far proposed to explain what the D-wave chip is doing have now been proven to be false by this paper. And most interestingly, I think these are actually the most intriguing results because we don't use the same basis for computation as the energy basis, whereas the gate model guys do. You can quantum anneal on timescales that are orders of magnitude longer than the so-called coherence time system, because the coherence time is a measure of what happens in the energy basis. We're not using that basis to compute. And those 2 papers show that. So the physics is pretty well established now. It's just an interesting device. So why is this really exciting? Well, this is one reason people are very excited. Our colleagues at Google who had our 1,000-qubit machine, previous generation machine. They wanted to determine whether the machine was doing quantum annealing or classical annealing. So they compared the running time of the D-wave machine to simulated annealing on the same problem. And they also compared it to quantum Monte Carlo, which was a classical simulation of the quantum mechanics of the chip. And what they found was the D-Wave machine was about 100 million times faster than a single Intel core against both those algorithms, which was very intriguing. In fact, it cost Google about $1 million of computation time just to get that graph. And if they repeated that problem with the new processor that they just had turned on last week, which is now 2,000 qubits, it would probably bankrupt Google if they actually wanted to do that computation. Well, people have looked at this and said, but there are more efficient classical algorithms for this particular problem. That's true, there are. But the reason Google or D-Wave aren't too concerned about those is you can show that the algorithms that currently compete well on this problem will not do well as we increase the density of connections in the chip, because the complexity scales as an exponential in a property of the graph called the tree width, and our next generation processor is going to have dramatically bigger tree width than the current one. The other thing you might see from this graph is it looks like the scaling in the D-Wave curve is parallel to quantum Monte Carlo. So some people have took this to mean that the D-Wave machine can be simulated classically just with a slowdown of 100 million. Well, that actually turns out to be an artifact of this particular problem. We now have lots of examples in which the D-Wave machine scales a lot more favorably than quantum Monte Carlo, which is extremely interesting if you're trying to make a simulation of a quantum Boltzmann machine. The second reason I think quantum computing is exciting is this graph. So what this graph shows is 6 different algorithms. The red dots are quantum, the other dots are all classical algorithms. And they're all solving the same problem, trying to find low energy solutions, bit strings that almost optimize the problem ideally. And a dot appears if you return a solution within the same time window allowed for all the algorithms. So what you can see is if you're doing global optimization, the trajectory you follow is these black lines. So if you're doing global optimization, the current D-Wave chip looks like it does about as well as this Selby algorithm. It finds the optimum at about the same time. But if you're actually doing sampling, and what you want is a lot of low-energy configurations in a short amount of time, then the D-Wave processor is dramatically different from everything classical that we have looked at so far. Now, you can use that classical sampling to great effect in machine learning. There's a class of models, undirected models, called probabilistic graphical models. And this was a model in which we actually picked a graph, and we picked the parameters for the model so we knew what the ground truth was. Then we draw samples from that model, and we tried to learn the parameters from the samples. And this graph shows the distance between the distribution the model has learned and the ground truth as a function of the number of model updates we did. The red curve is what the D-Wave solution does, and the blue and the green curves are what the current methods of persistent contrastive divergence and contrastive divergence do. Now what you can see is it's quite remarkable that the quantum seeded samples can cause you to learn the parameters far more quickly than TCD or CD can. So that's very encouraging. One thing we wanted to then understand in more detail was how's that really going to help machine learning? And this is really one answer to that. AI is not yet doing everything we wanted to do great. In particular, let me read this very carefully. Unsupervised learning had the catalytic effect in reviving interest in deep learning, but since been overshadowed by the successes of purely supervised learning. That's true. By like 90–95% of all the work in machine learning today is really supervised. The people who wrote this said, we expect unsupervised learning to become far more important in the longer term. And that's because the way humans learn is we don't learn from having labels of everything in our world. We learn from just the raw data. So who said this? Well, the 3 founding fathers of deep learning said this. And they said it quite recently, back as recently as 2015. And the reason we think quantum computing is exciting is just as the GPU was the workhorse that really has powered supervised learning, we think the QPU, the quantum processing unit, could be the device that really makes unsupervised learning feasible for the first time. And fundamentally, the reason it works is unsupervised learning can be based on probabilistic models. These rely on sampling to train them. And the quantum computers are native physical samplers. So the quantum computing is doing things physically that classical chips can only simulate inefficiently. So how does sampling arrive in machine learning? Well, here's a simple undirected model called a restricted Boltzmann machine. It has the structure of a bipartite graph. And to train this network, you are given a set of data vectors on the visible layer, and you have to adjust the model parameters so that the model most likely reproduces the training distribution. Right? And mathematically, what that amounts to is you have to maximize this log likelihood by computing the difference between two expectation values. One in the positive phase is easy to compute because it's conditioned on the input data, but the one in the negative phase is classically intractable to compute because it requires computing an expectation value over the joint distribution of the visible and hiddens. Okay, so you're basically computing over the model parameters. So we wanted to take that insight that we can do sampling better in this negative phase and apply it in a much richer set of models than just purely restricted Boltzmann machines. So here's a model that we have developed so far. It's based on an autoencoder network. So the idea behind an autoencoder is you want to train a neural network to basically learn the inputs it was shown. So if you give it a handwritten 3, after you train the network, it should produce a handwritten 3. You get a 5, it produces a 5. You get a 9, it produces a 9. And what happens here, what makes it interesting, is you restrict the middle size of the network, so you're forcing the network to learn a compact representation of the data. So if you took away the encoder and you just gave those vectors in the middle, you'd actually use this decoder to generate new digits, just like the ones that were handwritten. Okay. So one of the problems with these kind of networks is that the kind of data that we deal with naturally has both discrete and continuous characteristics. In the case of handwritten digits, the discrete characteristic is the identity of the digit. Is it a 0? Is it a 1? Is it a 2? Is it a 9? Right? The continuous characteristic is how thick are the lines drawn and what are the angles of the lines. So the data has naturally discrete and continuous characteristics. So the problem is with these autoencoder networks is you can't train them if you've got a discrete network in the middle here, because you can't backpropagate through discrete variables. So in this paper, D-Wave came up with a way of incorporating discrete variables into these variational autoencoder networks. So we call this a discrete variational autoencoder. And you can read the details in that paper. But the interesting thing is, having made this adaptation of these networks to include these discrete sampling problems in the middle, we can now show that this discrete variational autoencoder beats the state-of-the-art on 3 of the standard machine learning challenges, permutation invariant, MNIST, Omniglot, and Caltech Silvettes. And what's interesting is if we make this sampling problem in the middle based on discrete binary variables, like put a Boltzmann machine in here, we can get a discrete VAE. If we make the network samples from a quantum Boltzmann machine, we can get a quantum VAE. So we can basically make this hybrid network which has a quantum component in the middle and classical inputs and outputs. So it also means, for example, ours and everyone else's quantum processor is fairly small these days, but the networks we can build them into can be considerably larger. There's no constraint on how big we could make these encoder and decoder networks, so to sort of make them fit whatever quantum chip we can achieve. So you sort of see visually what this does is this is the previous state of the art on generating handwritten digits. This is the digits we could reconstruct after training. And then if you use that trained network to generate new digits, this is what you get. And they don't look too bad, but if you look closely, there's 1 or 2 digits here that really don't look much like handwritten numerical digits. On the other hand, if you use this hybrid discrete continuous architecture, you can train just about as well, but the digits you get have a lot more naturalness and clarity and a lot more closer to real digits to you. So this discrete network is able to do things that we cannot do as well using conventional techniques. And putting in the quantum sampling in the middle will take it to an even higher level. So the good news, I think, is that we are about sometime before Christmas this year, we're going to be releasing these web services for probabilistic machine learning. And these are services that are designed to make it easier for people to build and train probabilistic models. And part of the reason we're doing this is because GPUs have been so successful in the supervised learning deterministic sort of applications like classification, people have really lost interest in these probabilistic models, and we want to try to reinvigorate interest in the models by making these services available. And then as we develop the quantum processor further, we're going to infuse the quantum processor into these models more and more. But right now, the things that you'll be able to access is the best state-of-the-art version of what you can do in terms of classical Boltzmann sampling implemented in GPUs. The best you can do in quantum Boltzmann sampling implemented on CPUs, and then raw GPU samples from our current quantum processor. So all that will be available sometime before Christmas, and I'd really like to find people who have interesting machine learning models that have data that is uncertain or incomplete or has correlations that you want to infer from the data. These are all kinds of applications that these kind of probabilistic models would do very well. The nice thing as well is these tools are designed to be callable from TensorFlow or Python. So from the point of view of the machine learning developer, you don't really have to learn any new language or anything. You just make a call to these services as you would to other services. So that's pretty much what I wanted to say. We believe that quantum computing is most exciting because we think it can really turbocharge machine learning, particularly unsupervised learning. We have begun down this path to developing these hybrid quantum classical architectures. I'd say we're really at the beginning. There's still a lot of research questions to figure out, and we'd love to get smart people thinking about this. I'm most excited because with the quantum Boltzmann machines, we have a fundamentally new kind of machine learning model, because the distribution we're sampling from is a quantum Boltzmann distribution, not classical. And I do think if you have data in which the correlations arise due to quantum mechanical effects, and it may well be the case that a quantum Boltzmann machine is a more natural vehicle for learning those correlations, because as you know, quantum correlations can actually be in excess of those that you can have classically. That's why we have Bell's theorem, for example. We're going to be releasing these services before Christmas this year, and we've already shown that the DVA model can beat the state-of-the-art, and using the quantum sampling it should be even better. So let me know if any of you are interested in harnessing these services later this year. Thank you.
Hi. So, yeah, okay. I'll just. I was just curious. I think it's very interesting that in the Boltzmann sampling, it's you need to have this energy landscape, which is where the data is coming in, and so I'm curious. Also, in the analogy that you're making with GPUs, there's sort of it's very fast to compute, but then there's the kind of the overhead that you pay for like uploading the data. Can you say a little bit about when you upload some data or how much data, how that gets computed into the energy landscape and encoded into these, these coupling constants, and how slow or fast that is, and how?
Yeah. So the kinds of applications that this is best suited for are ones where the volume of data is not that large, because we're not set up to handle a lot of data yet. But we can basically configure these hybrid networks so that the size of the vectors you deal with can be very large compared to the size of the quantum processor, because the network structure is such that the quantum processor is only operating on a much fewer variables than what you can have as an input and output variables. So we are actually in a process of looking for cloud partners to basically build these services into existing cloud facilities so that we can tap into all the existing framework for all the data movement. Right now we have rudimentary tools for that, and we can send compressed archives around, things like that. But in principle, the networks themselves can be scaled dramatically bigger than the quantum processor. Yeah. That's a very good question, because you sort of identified an Achilles heel in a sense, because if you look at our duty cycle, the slowest part in our duty cycle is currently programming those parameters. It takes us 25 milliseconds to program one problem at the moment. So, and we know that we have to work on getting the duty cycle time down. The actual sampling time is ridiculous. We can sample in 5 microseconds, and we can read out in about 30 microseconds. So the actual running of the quantum annealing, the sampling is very quick. The programming is currently the slowest part. So right now, even though it is slow, we found applications in which high-quality samples, but fewer of them, get you more than lots of inferior quality samples you can get from an MCMC output. So it's a good question.
I was wondering, in terms of computing capacity, how does this compare with the gate model ones that the IBM and Google have? Because, I mean, you said ones that use gate model, then you need a lot of redundancy in qubits for error corrections.
Right.
And
yeah. So that's one of the things. I think it was it was really luck more than foresight. I think that the quantum annealing model is certainly resilient to noise to a much greater degree than the gate model. So you can actually scale up annealing-based machines to far larger sizes before you have to do any active error correction. We do no active error correction on our system, and we're getting correct answers to problems at the 2,000 qubit scale now. As we go to larger and larger chips, as we go to tens of thousands or millions, we might need to start using error correction too. But there are now schemes for doing quantum error correction in the annealing model as well. So we don't think we're at any greater disadvantage to Google or IBM from doing that. The big difference today is that the current machine we make is a non-universal quantum computer. So there's a particular coupling term from Hamiltonian we're not building right now, and it's either an XX or an XZ. We know how to do it. We actually have a design for how to do it. It's purely a business decision. We believe we can get to commercially relevant problems in machine learning and AI using the current architecture. So from a business reason, you do the simplest thing you need to do to get to a large addressable market. Now, the academic purists would probably want the perfect universal quantum machine, but it's going to be a lot more expensive and a lot more technical risk to do that. So we're doing this in a staged way. I think, in the next few years we'll be announcing what we're doing in the universal space as well. But it's not currently our top primary focus. Okay, thank you.
So we have a short announcement.